All right, so good morning, everyone. I would like to take your attendance first of all. All of you have come back. Let me see. Just wait. Ch.9, are you here? Ch.9.
Here. I am here.
Hi, morning. Xuân學家
Here.
陳家傑 鄧家傑 are you here? 鄧家傑何偉林
喺度。
林俊軒
Here.
林成漢
喺度。
係李佩恒
喺度。
鄧俊熙
喺度。
係鄧浩俊
你好。
係鄧浩俊係黃俊熙
喺度。
黃奕朗
早晨。
係早晨啊，石學明
喂，係。
係張思維
Hello。
係洪家軒
Hello。
何孝日係何麗賢
Hello。
係郭俊熙
Hi。
羅康力
Hi。
係你好，李晴
Hi。
係梁家傑
喺度。
係李澤星
Hello。
李建樂
喺度。
馬家樂
Hello。
係吳漢一
Hello。
魏俊滔Are you here? 魏俊滔 Yes。係譚君友
喺度。
黃成軒
喺度。
Okay, so we will have just remind all of you with this today after school we will continue our camp quiz right on on writing the ionic formula, okay, the chemical formula of ionic compounds. And for level 3 students,
sorry about that. I will be absent today because I need to go to hospital.
Oh, I see. So you have to maybe you have to wait until the next chance, right? Until you can get.
Or I just do before 1505.
1505, what do you mean?
Just in assembly.
Oh, you will have an assembly. So I can start it earlier. I can start it earlier. So I would adjust the time. I will adjust the time of the start of the exam because I've just scheduled the quiz event to start at 3:45. So I will push it 40 minutes before, such that you can do it at 3:05. Can you get my point? So all of you, please pay attention. The quiz will start at 3:05. Okay, I can start at 3:05. So I will give you 1 hour, and so that you can do it earlier, and you will have a earlier rest. Okay, can you get my point? So this is good news, right? Today is day 3. I'm still not so get used to new timetable. Even though it was once my timetable while I study in a secondary school, 6 days timetable. Now, anyway, and today we will proceed to get to know something about bonding and structures of the ionic structure. So what is so special about the ionic compound, right? There may be to the general public, we will try to think of some uses of it, right? Before that, we should know their properties, and more or less the properties, they are linked with the bonding and structure of those substances. Okay, so this is something a very challenging part, I must tell. Very, very challenging part for you to get to know more about the bonding and structure. In case you and today, because of that, I will give you one example, right, to talk about the bonding and structures and how does it relate to the properties of giant ionic structure, and we would get to know some other structure in the following lessons. Okay, so you know where we are now. We are having a small coverage of chapter 9. Okay, we jump to chapter 9 and go with a focus on giant ionic structure. So before that, I would like to show you a YouTube video, and it is something about something about visualization of what I would like to mention this. So I expect you guys to have read through those pages before we start. Okay, so let's see what is that, and try to tell me if you can listen to the voice. I just share the voice, share the audio. Try to see if you can listen to it. Yeah, can you listen?
So far, we have looked at ionic compounds as single entities. Ionic compounds actually exist as large 3D structures known as a giant ionic lattices. In this lesson, we will learn about, and you got it, these giant ionic lattice structures. When we talk about sodium chloride, there aren't actually any individual sodium chloride molecules. Instead, the sodium and chloride ions are arranged in a regular repeating 3D pattern known as a giant ionic lattice. Let's now have a look at the giant ionic lattice of sodium chloride.
So
we know that sodium and chloride ions are electrostatic.
First of all, you just mentioned one important point. It's about the form of sodium chloride. So it is, as I said before, it is rather misleading to tell you sodium chloride exists as a pair of molecules.
Instead,
okay, so this is what I would like to remind all of you. Because while you draw the electron diagram, very often the way to show the diagram start from this. Okay, for each sodium atom, it gives 1 electrons to chloride ion, and to form sodium chloride, and that type of relationship may be misleading to some of you. Okay, you may think that sodium chloride will exist as this, okay, as a molecule. Okay, so we will see the word one single entity, right? It is a unit. Okay, it is a separate unit. If you talk about it as a molecule, 分子, but indeed, it is not. Remember, this is not correct. Okay, this is not correct. For writing down this, they just show you the number of sodium ion to the number of chloride ion being 1-to-1 ratio. Okay, so what does it mean that they would exist as a giant ionic structure? So we will call that ionic lattice, okay, which is in form of a 3D arrangement. So this is what you may know it in the last lesson, right? So this is what I would like to stress it once again.
The sodium and chloride ions are arranged in a regular repeating 3D pattern known as a giant ionic lattice.
Okay, something like this. Okay, something like this. So you may see the arrangement of sodium ion and chloride ion, they are placed alternatively. Can you see that? One by one, okay? Positive, negative, I put it one by one. So this we call it is not just one plane, okay, one line, one plane, but also in 3D. Okay, so we would say in science, in mathematics term, we will call it x-axis, y-axis, and we will talk about it as z-axis, such that we talk about 3D. Do you know something about that term? Okay, something like this. So we call that a giant structure. They will place it alternatively. So remember, in this structure, as said before, we have got two types of electrostatic force, right? Can you tell me what are those two? We will call attraction, right? Do you know where is attraction, right? Whenever we have got two color or put it together, it is a type of attraction, right? This is attraction. This is attraction. This is attraction, right? Can you get my point? But at the same time, we would have it recorded as repulsion. Where is it repulsion? Between what? Now, for example, sodium ion versus this sodium ion, right? Repulsion, because they are of the same charge. Repulsion. So this structure is just the equilibrium. Okay, it's just the equilibrium of taking a look of attraction and repulsion. Of course, if you talk about this, of course, you may find that attraction force should be more than repulsion. Okay, we get my point. Such that it can still hold those atom ions together. Can you get my point? So this is what I would like to remind all of you about this. Any questions so far? Okay. So if not, I would like to proceed next to it.
Let's now have a look at the giant ionic lattice of sodium chloride. We know that sodium and chloride ions are electrostatically attracted to one another. Because of this, you will see that the ions are arranged so that the sodium ions are always next to the chloride ions. This arrangement is seen in all directions of the 3D structure. The electrostatic attractions in a lattice structure are very strong. Let's think about it. Each sodium ion is held in place by the electrostatic attraction of 6 neighboring chloride ions in all possible 3D directions. And similarly, each chloride ion is held in place by the electrostatic attraction of 6 sodium ions, also in all possible 3D directions. Since this lattice structure is so strong, it explains some key properties of ionic compounds. Ionic compounds have very high melting points. This is because a lot of energy is required to overcome the strong electrostatic attractions holding the 3D lattice structure in place. Ionic compounds are also very brittle. This means that they break rather easily into small pieces. A ceramic flower vase is also brittle. If knocked over, chances are it will break into small pieces. But why are ionic compounds brittle? When a force is applied to the 3D lattice structure, it will disrupt the regular repeating pattern of sodium and chloride ions. So the sodium ions are forced to be next to other sodium ions, and the same is seen with chloride ions. Like charges repel one another, and this repulsion essentially breaks the lattice structure. In summary, ionic compounds exist as giant ionic lattices, not as single molecules. The giant ionic lattice is a regular repeating 3D pattern of alternating positive and negative ions. The electrostatic attractions holding the structure intact are very strong, and this accounts for the fact that ionic compounds have very high melting points and are brittle.
All right, so we have just mentioned 2 properties. Okay, you talk about giant ion structure. Anyone who can tell? We've got 2 properties mentioned. What are the 2 in the video?
Very high
melting
melting
point.
point and brittle.
Okay, very high melting point and brittle. Okay, so whenever, and second, do you realize that if you were talk about the properties for the explanation part, what happens to the video? It will show something to you. It will, what will be the diagram that show you? They will show you something like ball, right? They will show ions and everywhere. So it will just explain you once again that if you want to account for the difference in the properties, right, of those substances, you are going to relate to something what we call it as submicroscopic viewpoint. Okay, something you need to deal with something that we cannot see it so clearly, but you use what? We use the diagram to illustrate your answer, to your understanding. Okay, can you get my point? So this is what I would like to talk to you about this and give you have a start. And next, I would like to show you something more about the textbook. Do you see this one? Giant ionic structure. So indeed, once again, if you want to talk about the giant ionic structure, we would have a structure like this. So different materials will have a different arrangement. If you want to talk about, even though you talk about ionic structure, ionic bond, it's not just that fixed. What do I mean by that? Is that structure is only applicable for sodium chloride, okay? But and also some other ionic compound with similar similar chemical formula, as well as the size difference between them. So remember, for sodium chloride, the sodium ion, the size of sodium ion is smaller than chloride ion, so they can put it just inside the hole. So I would like to present it like this. If I show, this is the one of the phase, right? You talk about this, so you may find sodium chloride being here, right? So you may find that we have got these 3 and 4. We have got this, right? So this, the first one I would like to show you is on the green one. The green one, the cube structure is something like this. So this is chloride ion. Okay, while sodium ion, the size of sodium ion, I would like to follow it by putting it as a purple color, right? Purple. While the purple, where you find it? It will be here. So what happened to the middle? The middle, is it the purple one or the green one? Can you tell? According to this diagram, the green one is still chloride, right? So I would like to mark it as chloride as well. Can you get my point? So each phase, we have got 6 phases. Each phases, they were having this similar structure, and you know what is mean by the size really matters, okay? The size of sodium ion is quite small when you compare with chloride ion, so they can be placed just like between the holes of chloride ions to make the structure more packed. Okay, that structure is more packed in structure. What to compare? If you want to compare with this structure is cesium chloride. So the difference is that for the sodium ion, change it to cesium ion. Now both they belong to group 1, cesium and chloride and sodium also belong to group 1. But the size of cesium ion and chloride ion is comparable, which means the size of them, they are very similar. They are similar in size. So what is the consequence? Is that if you want to stick back to this type of structure, you may find that if I imagine this one is cesium ion, so the hole itself is not big enough for it to insert it in between the chloride ion. So can you get my point? Instead, what will happen? The whole structure will be loose, will be more loose, will be less lightly packed. So we will find it seems like the chloride ion, right? They are trying to make the hole bigger, right? To make the space between the chloride ion bigger. So you have got another structure. Can you see that? So what by showing this 2 structure, what I want to tell you is that if you want to talk about the packing of the giant ion structure, it's not just definite one structure. We have got so many different type of structures. So we have to consider 2 ways. Okay, this one is less packed structure. Less packed structure. So if you want to talk about the packing of it, we need X-ray for help. Okay, we need X-ray for help. I shine an X-ray through a crystal, and from the electron density. Now, this diffraction pattern, you talk about something about the electron cloud density. Okay, so you talk about the spread of cation and anion, and such that they can derive and think of the model, right? Okay, like this. Okay, can you get my point? So in short, the structure, the packing of ionic structure, we will say it as giant ionic structure depend on what? Depend on relative size of cations and anions. So you talk about the ratio of size actually in university study. Second, you may get to know something about the mole ratio, number ratio of cations and anions. If you talk about this, the structure is different. So what is mean by that is not necessary to be 1:1 ratio, right? 1:1. It can be 1:2, 2:1, etc. So it will give you different type of structure, except before last time. Can you get my point? So how about in DSE? How many different structures do we need to memorize? Do you know? The answer is just that 2. Okay, don't worry. We need to you need to know how to draw this structure and this structure. Okay, in short, in simply speaking, you may use this one, right? This one is a simpler version of telling that 2 structure. One is sodium chloride, the other one is cesium chloride. Okay, so what is that structure? The structure, they would widen they will widen the spacing in reality. It's imaginary model, okay? While you will see how those ions they are packed in 3D sense. So we would say this type of model a ball and stick model. Okay, we call it ball and stick model. While you talk about this one, we call that space filling model. So more on telling you the reality here, right? But once they are too packed, you may find it very difficult to get to know how they are arranged. So here comes this model. This is ball and stick model. So no matter what model we are having, so what they are having similar is about the arrangement. So you may find that sodium ion, which is cation ion, positive ion, and chloride ion, which is negative ion, they are placed alternatively. Can you get my point? You got it?
Yeah.
Yep. Difficult? Any questions so far? Anything that you want to ask before we proceed? No? Now, if not, I would like to go back to the two properties that I mentioned, right? You talk about their properties having the following, okay? So you may see it, the best way is to generalize the properties of ionic compound properties, 特性. Okay, so what is mean by 特性 property? It can be what? As said before in Form 3, it can be something as physical property and something like chemical property. Okay, but in this topic, in this chapter, we focus on physical property only. Okay, biochemical property depends on the chemical itself. Okay, so there is no special pattern. But for physical property, they have very similar pattern. So in this following pages, we will talk about the physical property. Such like melting point, boiling point, very often we would stay together for explanation. And together with stage, okay, all those belong to the same thing. Okay, we will talk about it all together. It's the same concept. 2. Solubility in water. Okay, in water 溶喺水啊，水溶解毒. So if you talk about solubility of water, very often we need to have a definition. The definition is certain temperature per 100 grams of water, how many grams of the salts can dissolve. Okay, can you get what I mean? So because how much salt can dissolve really depends on how much water that we have as well as the temperature. Okay, the higher the larger the portion of water, of course, it will dissolve more. And at the same time, the higher temperature, the solubility of the salt will normally be greater. Okay. Yes. Sorry.
Why in high temperature can more salt be dissolved?
Okay, a good question. So after you know something about the solubility, what happens about it being soluble in water, I will explain you more about this later. Okay, after you know what is the principle behind about solubility first. Okay, and this is something about the difference. And number 3 is on the electrical conductivity. Okay, 導電性. But remember, starting from today, if you talk about electrical conductivity, we cannot say it as conductor or insulator only. Okay, we need to mention it a concept of electrolyte. Why? Because electrolyte is a special case. It can conduct electricity while in molten or in aqueous solution. So that is the definition of electrolyte. Okay, so never you just tell me that sodium chloride does not conduct electricity. Okay, no marks. Okay, because you have that type of statement is conditional. In solid, your statement is yes, but in aqueous solution or in molten state, the answer is no. Okay, so this is what you may talk about the general properties. So you may relate this to the key point here, right? I have a high melting and boiling point. What you mentioned is about the 1 on top, usually soluble in water. You talk about 2 and 3. They conduct electricity in water, and the dissolved water is 3. How about here? How about hard and brittle? And you will know it in the following pages. Okay, remember all 4. So this is what you may know about the first part. So if first of all you talk about melting point and boiling point, it's easier start. Okay, it's an easier start. So can you write down something about particle wheel point here? Okay, on the left hand side, you may see some space here, right? So if you have the notebook with you, it is better to copy it down. And in particle wheel point, can you account for the high melting point and the boiling point of those? Okay, all those they are just explanation, but the best way is to take a look on is 1-1. Yes, you just draw something like this. Okay, what is that? They will show you something in particle wheel point. Now, I just want to simplify the whole thing by drawing a 2D diagram. Remember, indeed, in reality, we have it in 3D. Okay, so the first point, there are strong ionic bond between the ions with opposite charge. Okay, so can you see the word? So what does mean by that? In this diagram, you may see the attraction. They are being held so strongly such that it is type of a strong attraction force that will holding the ions together. Okay, so you may see that that it will give you a regular arrangement. In order to melt or boil the ionic compound, they would overcome what? They will overcome the strong ionic bonds between the ions. So how? I can supply energy. I supply energy. So what can be form of energy? If you talk about melting and boiling, it is in terms of heat. Okay, so heat, it is a form of energy. What happened to this? In order to make it more what? So just imagine what you understand about Form 1 IS. What happened if it is still solid? If I increase the temperature, what will happen? Temperature increase, what will happen to the particle? 我問翻啲 Form 1 IS 嘢先。
Move more rigorously.
Okay, move. Move is solid. Would they move? It is solid, right? Do they move?
Vibrate.
Yes, they will use the word vibrate. Vibrate, which means they just shivering about its own position. Okay, 喺度震嘅啫，震動。So vibrate, the temperature increase, they will vibrate more. Okay, they will vibrate more frequently, for example, or violently. Okay, in terms of the distance. They will wait until the heat is enough, okay, for it to really overcome. Okay, overcome, which means the energy of it is high enough to oppose that type of attraction. So what will happen? So they can make the ions free move. Okay, so during melting, the energy So what will happen? They will start to move, right? Such like this one, they will move it here, move it here, move it here, right? So you can move freely. So if we can move it freely, what is the hidden message? That the attraction force between the ions are overcome. So of course, if you want to talk it as melting, you need to overcome some of the attraction force. So remember, that type of attraction force, what is that? It is the ionic bond, which is rather strong, as reflected in the relatively high melting point. Can you see that? The melting point of sodium chloride is about 800, 700, 700, even 2000. It's rather high. Well, to compare with such like water, the melting point of water in terms of ice, right? Ice melts with water is just 0 degrees. No need to mention something like oxygen gas, nitrogen gas, etc. Okay, the melting point of it is as low as minus 200 degrees Celsius. Can you get my point? So can you imagine the difference? Okay, so the force holding the ions is rather strong. So in order to melt it, you are going to overcome certain type of strong attraction force in terms of ionic bond between the ions. So in order to melt, okay, in order to let it move it freely, sorry, you need to have a quite large amount of energy. Can you get my point? So similarly, if you talk about boiling point, the case will be more vigorous, that you need to have more energy if to overcome almost all attraction force. Remember, why do I say in liquid? In liquid, take a look. In liquid, there will be something like this. Okay, they will be freely moving. While if you talk about boiling, so what will happen to this, to the positive ion and all those negative ions? They will move more freely apart, okay, with the spacing. If the spacing even more spread, okay, larger spacing. So having this, we will see that almost all attraction force is overcome. Can you get my point? How about this? From solid to liquid, partly. Okay, partly overcome. Can you get my point? Only by having partly overcome will it make the free moving, but not separate those ions totally apart. They will not leave. Can you get my point? So it will tell you the difference between the melting and boiling. Both of it will overcome the attraction force, but the amount of attraction force to overcome is different. Of course, during boiling, you need to overcome more. Nearly most or attraction force will be overcome. Do you understand? Do you understand? For those who don't understand what I just said, could you please put a tick? If not, cross. And you may feel free to ask questions here. Partly about, nearly 19 of you would understand. How about the other people? 20, good. Now, if you really understand, okay? You really understand? If so, that's my turn to ask you questions. Get ready. 譚君佑
Hello.
Hi. Now, could you please account for the difference in the melting point between the substances like sodium chloride, okay,
Okay.
and the other one, it is potassium chloride. Why do I have a slight difference in the melting point? Now, let me put it this way. If you do not, and similarly, I can do the same by asking you, sodium chloride is a melting point of 808 degrees, but how come aluminum oxide would have a very high melting point? Can you think of some factors affecting the strength of ionic bond? Let's try. What do you think? Now it's just not the pressure is just not on you only, okay? For the others, you may help. Just wide guess because no other information given. I just give you this. You may think of some other factors. Yes.
I think I think is related to the ratio.
What ratio?
Of the cation and the anion.
Or the number ratio, you mean?
Yes.
The number ratio. Okay. The number ratio, they will tell you the number of relative number of cations and anions. So can you elaborate more?
I guess lah.
All right. So how about you may have heard of something like the ratio of cation and anion. What else?
It is related to the original reactivity of the elements of the compound.
Okay, now I mark it on the book first of all. First of all, somebody would think of the cations to anions number ratio. Something you talk about reactivity. Okay, what else? What else? And tell me.
Yes.
What do you think? The questions is about to account for the difference in melting point between those ionic compounds.
Yes, I know. I can't think of any.
You can't think of any.
I can't think. It's related to the atomic size.
Atomic size. Okay, atomic size. Atom. Is it in terms of atom? Now take a look on that. Now, first of all, let us rule out some of the possibility. We are going to talk about melting point and boiling point. During melting and boiling, is it a physical change or chemical change?
Okay.
Physical.
Physical change. So what is the difference between chemical change and physical change? Is that any new substances will be formed, right? The answer is no. So it is nothing to tell about reactivity. Okay. Second, if in order to get to know the melting point, it is all or less reflect the amount of heat needed to overcome the attraction force. Can you get my point? Based on this concept in mind, can you tell the strength of ionic bond between their four substances. Which one has the strongest ionic bond?
Aluminum oxide.
Yes, this is aluminum oxide. So both four the ions, they are bonded by ionic bond. But this one, you may know that it's the strongest ionic bond. So what is the nature of ionic bond? As I said before, what does it mean by ionic bond? Ionic bond is a type of,
The electrons is
what is that? We will call this term, right? Electrostatic attraction. Electrostatic attraction. Okay? So all of you, could you please, I will give you some time, right, to search it on the web. Tell me, if you type electrostatic attraction on the web, what will you find? Actually, you will find very different things, just like what you know it as 靜電, just like a spark in a dry condition, right? But can you type one more key term, which is formula? Formula, a type of mathematical relationship. So what will you get? Okay, what will you get? Tell me, and use this equation and you may know. Mr. Chin, do you mean that we need to know something more about this? A little bit, but not too much. You need not know the formula, but once the formula, indeed, they will help you relate them. Electrostatic attraction and then formula, and try to see what we will get. Okay, so what will you get? Can you see one term? Coulomb's law. Can you see what is that? Don't be afraid. Something about physics. Oh God, I don't want to see that. Okay. Just focus on this. Can you relate once again? What are the factors? If you put this into ionic bond, can you tell me what are the two factors affecting the electrostatic force, the strength of electrostatic force? The two factors.
the charges of the ions.
Good. Charges of ion. What else?
The distance between the cation and anion.
Yes, if you talk about distance between cations and anions, so what is that? What is that? We will talk it as, sorry. So we would talk it as a cations and anionic size. Okay? So finally they will come very, very close. So close that it seems like it's touching, right? So simply speaking, there are two factors affecting the strength of ionic compound. The first one is the charge. The other one is the size of cations and anions. So if you talk about size of cations and anions, that contributes to the distance between them. Can you get my point? Easy, difficult, or what? Now, don't worry about physics. Indeed, the rule itself is just a tool for we to understand. Okay? We need not memorize this. But once you know that, oh, I know something more, it is backed up by some theory behind. Okay? It is a type of mathematical relationship. Can you get it? So I would like to simplify this one into the following. I would like to simplify this as the factors. The ionic bond, they were attracted, there are several factors. They are affected by this. Sorry, wrong arrow, wrong direction of arrow. I may do it in reverse. The strength of ionic compound. This time, I would change it to ionic compound. The ionic bond, right? The strength of ionic bond depends on what? As said before, F. Just remember the formula. is proportional to Q, the charge, positive and charge negative, right? And the distance, what is the distance? The distance between cations and distance and anions, okay? Do you still remember that formula? Don't worry about the K, it's just a constant, right? So I just pick up that two important terms. So what is that? The charge of ions, both cations and anions. And second is the ionic size, okay? And that too, they would affect the strength of ionic bond, okay? They would affect the strength of ionic bond. Can you get my point? So what's next is to get to know the change, okay? So from this equation, it can also help, right? In case the size, in case the charge of ion is greater, so the ionic bond will be stronger. Can you get my point? So it is all more or less reflected by this part. Can you see on here? So aluminum oxide and sodium chloride. Okay, sodium chloride, they have just the charge of +1, -1 only. How about aluminum oxide? Is +3 and -2. So of course the ionic bond strength will be greater. Second is ionic size. If the ionic size is smaller, the ionic bond will be stronger. Okay, why? Of course, it is easily understood. The ions is packed more closely. Okay, the ions, they are packed more closely with the small size. If you want to talk about big size, okay, so the way to overcome these two will be more. Okay, can you get my point? So, of course, this is just a general way to compare. There may be some other factors that may affect, just like packing. Okay, packing doesn't tell. It doesn't tell you anything about packing here only. So you need to know the packing of those different substances in nature in order to tell the very minimal difference between the two. Now, for example, magnesium bromide. Okay, so you may find it is 711 degrees Celsius, but you may find that magnesium ion is it have a higher charge, right? But that two size is large. Okay, so we have got two contradictory factors that may affect the overall ionic bond strength. Right, one of them, the charge higher, the bond will be stronger, but the size of ions is larger, the ionic bond will become weaker. Can you get my point? So it two contradictory factors that will more or less affect the outcome. But using this diagram, we give you a nice flow, okay, a nice guess that the ionic bond, okay, different materials will have different ionic bond strength, so they will have different melting point. Level 1, just understand this. But if you want to get to know why, now level 2, here comes, we have got some mathematical relationship, and use this something about physics to help you understand the strength of ionic bond and how is it affected by it. Do you understand? Easy, difficult, or what? Now, leaving behind is on the other 1, 2, 3 factors. Okay. Any questions so far? First of all, we have got those. Any questions? Now, if not, shall I elaborate more on other factors before we end the lecture, and then we'll spend some time on doing the exercise together because it's rather difficult and abstract. Any questions so far? Now, second is about hard and brittle. So you need to memorize the whole flow of this diagram as well. Why? In your exam, you did not draw this, but this will help you this will help you understand this. Okay, so in exam you need to write down this, but if you draw this, it will help. Okay, now this diagram is different from what you will see in YouTube. You see that in the YouTube, the way to present is much different. They try to put cations and anions apart, but it's not the case. Indeed, if you want to measure about hardness and brittleness, so it is something about the something about physics again. How do I know the substance is hard? Can you tell? How do I know actually? Only by seeing, and we will see that this substance is hard. No.
Density.
Density, is it?
Yes.
Okay, density. Something hard and density is interrelated. Do you mean something like this?
Yes.
Yes. Okay. How about wood? Wood is also hard. How come it flows on water? Can you get what I mean? So hardness and density, the way to measure is different. Okay? How to measure hardness in science viewpoint? How do we measure hardness? Do you know? A motion of ions don't move much. Okay? When you do something, actually, hardness, can you just merely see it? The substance, I can tell it is hard. Can you get my point? When I see a piece of chalk, by looking at the appearance, can I say that it's hard without touching? Can we say for sure? The answer is no. Can you get my point? So if you want to talk about hardness test, so what is that? Hardness test, it is something like on the, I would like to mention it as the, on the left hand side. Can you see the page? Can you see the picture? So hardness test is you need to apply a force. Okay, you need to apply a force towards a piece of material. How? The one on the left-hand side is frequently used as a model. Okay, you may copy it down. The one on the left-hand side. So what is that? This one. So this one. So what is that? It's a typical hardness test. I used a piece of diamond. Okay, you know that diamond, it is the hardest substances, naturally occurring substances in the world. Okay, hardest natural substances. So I use this to fight against the material to be tested. So of course, some other substances, while it is under the pressure of the diamond, they will change shape. Can you get my point? Do you understand? Just like the people in the past, the Asian Chinese people in the past, they will have some gold nugget for paying, right? So they would doubt whether or not the gold is real or not. So what do we frequently do? 係咯 Why? Because they use their experience to tell. Different materials, different metals, once I apply a pressure to it, they will finally leave some small, a little bit changing in shape. Okay, so according to the experience of breaking them, okay, the force of breaking them, they are trying to relate to the purity of gold and use it to tell whether the gold is real or not. Can you get my point? So something similar, I use the diamond. Actually, in Western side, they will use the diamond instead of the teeth to use, right? If the material is too hard, so what will happen? So I press it hard and try to see what we call it as the depth of impression. Okay, they will give you some mark. The depth of the mark, the size of the mark, they will tell how hard it is. If you talk about hard substance, what is that? If I talk about it's hard, the mark will be smaller, right? If the substance is soft, it's not hard enough, they will leave a very large impression. Can you get my point? So it, of course, it is more or less depend on the force. We call it the load, what we are now applying. In order to have a fair test, of course, this load, the mass of the load is the same. I use this fair comparison to tell the hardness, to compare the other substance. Can you get my point? So what do I know in reality? In reality, while you talk about the substance being hot, we are going to have the following. We are going to tell the motion of pushing. Can you see that? Of pushing certain array of cations and ions. Whenever you talk about hard and brittle, just imagine you are having a hammer, right? Try to hit it. Okay, if it is hard, what will happen? That the shape will not be changed. But if you want to talk about brittle, what is that? Now, in hardness, if you hit it, they will not change the shape. Okay, not change its shapes easily. So if you want to talk about brittle, it is another concept. It is 脆, yeah. So which means that when I break it, okay, so what will happen? They will be separate or broken down into pieces. Can you get my point? They will separate into pieces. So for the substances which is hard but not separate into pieces, we usually describe it as strong. Can you get my point? Strong and hard is different, okay? Hard, strong. And for example, iron is a hard and strong substances. But if you want to talk about the chalk, a piece of chalk, blackboard chalk, it is hard but brittle. Can you get my point? It's different, okay? So what is said as brittle? Brittle is a property, a very typical property, which means that for other substances, it's not brittle. Only ionic compound is brittle. So ionic compound, it is a lattice of alternating means one by one, okay? Positive ions and negative ions, we put it into a lattice. Once I apply a external force, so the layers of ions, underline the term, may move relative to each other, okay? May move. They will slip, okay? They will slip over. That type of layers of ions, they will slip over one over another and wait for a moment when they would have a repulsion between the same charge. Okay, once we have got that occasion, what will happen? They will cause the lattice split. Okay, so we will call that brittle. Can you get my point? So we focus on what? We focus on the charge here. The charge here. Can you see that? What I write down the charge? What are they the same? Okay, they are the same charge. So once they have a moment after a slight move, they will have the same charge coming too close. So what will happen? They will repel. The verb of repulsion. Okay. So they will separate. Can you get my point? Understand? So remember, hardness, brittle. They are hard but brittle, but it's not hard and strong. It's hard but brittle. It's a very typical property of ionic compound. Understand? In this chapter is very, very hard to understand, I must tell. Very, very hard. And we have got high melting point. This one is rather difficult. I will come to here first. electrical conductivity. As said before, the ions, they are held together strongly at room temperature. Okay, so the ionic compound, they do not conduct electricity in solid state because the ions, they are held in fixed position. They are not free to move around. So we say that it is not electrically conductive at solid state. But if you want to talk about it as molten state and in aqueous, all of you please write down, in aqueous solution. So what are they in similar? So you may see it on the diagram here. Is that the ions becomes what? Mobile. They becomes mobile. They can move freely. So under the influence of electric field, they would go to the directional position. Okay, so the directional movement of charge, we call that electrically conductive. So if the whole circuit, I would put it in a light bulb to tell whether or not it conducts electricity. The lighting of the bulb, they will tell us that the ions, they are moving directionally. 有方向性咁喐. Okay, so you may see that how the cat ions, they will move towards a negative electrode, but the N ions, which is negative charge, move towards the positive electrode. Okay, can you get my point? So the keywords, what is that? When you talk about the ions which will help conduct electricity, I need ions to be mobile. Okay, but for solid, the ions are there, but the ions, they are not mobile, immobile, so they cannot conduct electricity. Okay, they just vibrate. They will just vibrate in a fixed position, so they cannot move freely to carry the charge. So we cannot say that the ionic substance at solid state conductive. Can you get my point? Questions? So it seems that Mr. Chin, are you going to tell me that those small paragraphs should be memorized, should be recited? The answer is yes. But wait a minute, it's quite difficult to recite, so what can we do? You better take a look on the diagram, and diagram really, really helps. Can you get my point? So that's why if you want to study that topic well, you need to have a picture to visualize your memorizing. Okay, this is one of the techniques of studying. Okay, some other mode, right, which will help you understand what is that. Questions? Now, finally, it's about solubility. Now, solubility is a rather complicated concept. In order for the substance to dissolve in a solvent, you are going solvent. So indeed, what is that? We talk about water as a solvent, right? The one which make the solute to form a solution. So if you want to test it, to test the material being soluble or not, okay, we would tell the ionic compound as solute. I try to test it as a solute, and I put it into a solvent water. In order to dissolve a solvent, you need to overcome what? First of all, the attraction force between the particles and the solvent particles. Okay, they are strong enough to overcome the attraction force between particles in the pure substances. Okay, so please take a look at that. Particles and solvent particles, they are strong enough to overcome the attraction force between the particles in pure substance. Wow, very difficult to comprehend. Okay, second, the particles in the substance must separate from each other and become surrounded by the solvent particles. So we will call that a type of solvation, or a type of the ion, the attraction between the ion and water. Okay, ion water, that type of attraction. Can you get my point? Okay, so we will call that the ionic compound being soluble. Remember the word most. There are some counter-example exception. For example, calcium chloride, it is not. Calcium carbonate is not soluble in water. Indeed, it's ionic compound, but it's not soluble in water. But most ionic compound is soluble in water. So we focus on what? We focus on attraction force. Can you see that? If you don't understand this part, don't worry. You may see the diagram here. So first of all, if you talk about solvent, we may know water as an example. Look at the water molecule in more detail. So water, we will call a type of a polar substances. Polar, we call that 有極性. So we call that a slight charge of the molecule. Itself is neutral, but we have got certain part which is slightly negative. But it's not a total charge, it's slight charge of negative at oxygen atom, while hydrogen atom being slightly positive. So we will say that slightly negative, slightly positive, and okay. Remember, slightly negative, talk about O, slightly positive, we call it about hydrogen. Okay, so why is it like that? Indeed, we have got the bond. The bond is held by electrons. So the electrons, they come much closer to the oxygen. If you don't understand what is that, just imagine it as a type of bar magnet. Okay? So you want to talk about dissolving, what is happening. So this is what I would like to ask you guys to memorize. The negative end, the slightly negative end of the water molecule, they will attract what? They will attract positive sodium ions sufficiently to remove them from the lattice. And then the sodium ions, they are then surrounded by the water molecules. Similarly, the positive end of the water molecules, they attract the negative chloride ion to remove the lattice and then become surrounded by the water molecules as well. So what does it mean by that? Indeed, those water molecules, they will hit the surface of the sodium chloride. So what will happen? So they will pull away, for example, they will pull away these and to form this. So once I pull it, it's not just one-to-one. That sodium ion will be naked to them and another into the surrounding water. So they will have that type of attraction. Okay, they will have a surrounded by certain attraction force. Okay, you get my point. Similarly, if you want to pull away the chloride ion, I need the positive end, like this. So once I put it, I remove the chloride ion outside. So the water surrounding water, they will surrounded by the water molecules like this. Altogether, we have got 4 water molecules. Can you see that? And here, similarly, we have got 4 water molecules surrounded by 1 sodium ions. But indeed, it's just 2D. In 3D sense, we have got top and below. It's about 6 molecules actually. Top and bottom. Can you see that? Top and bottom, we have got 2 more. So it is a type of telling you it is a type of solution. Okay, but ionic compound, they are usually insoluble in non-aqueous solvent. Non-aqueous solvent. What does it mean by non-aqueous solvent? Just like thinner 水, it is one type of example, non-aqueous solvent. The solvent, it is liquid, but it is not made up of water. Thinner 水. The other one example that will show it is cyclohexane. You may find it is very difficult to understand. And another type, smelly solvent. Very often, if you talk about non-aqueous solvent, sorry, I write in the wrong way. 環己烷啊，環己烷. Okay, so it is a type of non-aqueous solvent. So why? They are not soluble in it because the ionic bond is too strong when you compare with the ions, attraction between ions and the solvent molecule. They are not alike, so they would not pull the ions out of the lattice. So it is a type of a stress. It's a type of force. If the force they are alike, they would be doing something alike. Okay. Okay. The forces they are alike. Okay. Very similar. It seems like positive ion, negative ion. They attract, so they would be pulled away so easily. But for non-aqueous solvent, very often it is said to be non-polar. Non-polar, which means something neutral. The neutral particles, they not pull those ions apart so easily because it's too weak. The force of them is too weak. Can you get my point? So I just stop it here. You may find it very, very difficult, right? For a time being. Huh? So what I've just mentioned about the four properties of ionic compound. First of all, have a brittle. Second, high melting point, boiling point. 3, soluble in water, but not insoluble in non-aqueous solvent.
Mr. Chin.
Yes, and
The
for
book,
yeah.
The book says that usually. So is there any exceptional case?
Usually what? Usually
Usually
soluble.
insoluble in non-aqueous solution.
Oh yes, yes, yes. We have got so many exceptions actually. Don't worry, don't worry. You will know it one by one. Okay, you will know it one by one. So most of the time, I must tell, most of the time, ionic compound is not soluble in non-aqueous solvent. But finally, if you want to talk about solubility in water, I must say that not all ionic compound will be soluble. Okay, don't worry, you will know it one by one. Okay, because on non-aqueous solvent there are so many examples. If you talk about some non-aqueous solvent but a little bit polar, but polar solvent, there may be a chance. Okay. For form 4, it is for form 4 it is 29. You need to. So take a look on past practice 9.1. Okay, so it's time to try it by yourself. Okay, I'm sure you can make it. It is something about drawing electron diagram, diagram of a setup to do electrolysis of the aqueous cesium iodide solution. To tell me the bonding is ionic, to tell me explanation about electrical conductivity. Okay, so this is the first task. And if you go over to the questions in this chapter, I will select some of the questions about this. Okay, don't worry, we will go back to this later when you do the overall comparison. You will can you see that something about ionic bond? You may see some questions about ionic bond. But if you talk about comparing this structure and another structure, we will leave it later. Okay, this one is ionic bond. So don't worry too much, and to account for the difference in the properties. Very often it's a type of comparison questions. Okay, but for this part, this question, for example, it is ionic compound. Okay, so I will circle some of the questions and place it onto the Google Classroom. Okay, as an assignment, and I will like you guys to do some questions. Okay, and let me know your understanding. Okay, now can you see that? Wow, so you will have a more challenging life in the coming lessons. All right? So what do you think about today's lecture?
Mr. Shi, before end, I
Yeah.
would like to ask one more question. Is that
Yeah.
you have said that
Yeah. What is that? What do you want to ask?
solubility,
Sorry, I cannot hear.
solubility,
Solubility, yes.
yes, and they are surrounded by 4 water molecules. So will there be any other substance that is surrounded by more than 4? And
Now, indeed, it's not just 4. It generally is 4 or even 6, because if you will talk about 3D, 3D is 6 but not 4. Now, what you see is on the 2D diagram. So in reality, the solution is in 3D. The solution is in 3D. Can you see that? It's just a 2-dimension. So you are going to talk about 3D. So you talk about top of the sodium ion and the bottom of sodium ion, just like in the paper, above the piece of paper and behind the piece of paper. So not, in general, we have got 6 water molecules surrounding it. But do you mean that those surrounding water molecules will not move away? The answer is no. They will also move away. Okay, they will also move away. Once they move away, what will happen? They will be replaced by another water molecule. Okay, can you get my point? So it's not just surrounded by that and they will not leave. Sometimes they will leave. Okay.
okay.
Yeah.
Oh.
How about the others? Very difficult, I must tell, for this chapter, because you need to get to know more about the structure, bonding. And what is that? Indeed, well, we just have a, just keep this in mind. It seems that we attempt to talk about the physical property of a substance, while the physical property would explain by what? By the material itself. What do I know about material itself? It's related with the bonding and structure of the substance. Okay, they would help determine the physical property. So this is the core concept today. Okay, so we will use this type of concept to relate to some other materials. Okay, why we will find that so difficult? Why you find that so difficult? Is because you now have something submicroscopic, okay, to relate it something about macroscopic. Do you understand? So this is what is challenging. Because something submicroscopic is you cannot see it. Some macroscopic you can feel it by experiments. So this is why we find it difficult. All right. Okay. I will just stop it here and see you guys 2 days later. It's Wednesday. Okay. Bye bye. Bye bye.
Bye-bye.